is an amazing question. Hey, guess what? This meeting is being recorded. Oh, no. Okay, so let's talk about schedules first. All right, so if I put exam 4 on Wednesday. All right, so exam 4. And Wednesday will be the 7th, 8th, right? And that will go through 22nd. What is the Monday after the break? Okay. See, but that goes right into finals week.
Right. Plus we have to do 2, or if we're gonna do a gel, I mean, we already have 2 exams, 2 finals we have to do.
All right, nobody wants to do an exam over the break, but
how much material do we need to cover before we do exam 5?
11. And we're finishing 10 today, and we'll finish, so you will have enough knowledge by next week to finish exam 5.
We were starting chapter today.
So we'll finish this is the really long chapter. We should be able to get through the other 2 by the end of the week.
So one thing I'm asking is, can we put more material into the quizzes and value the quizzes a bit higher?
Or do we
Oh.
cancel the one meeting? Yeah.
Oh.
Yeah, but
Or just have it open for 2 weeks and then open exam 5 a week early and have that open for 2 weeks. Even though they will be overlapped.
So they're overlapping.
Yeah.
Jessica.
So I was gonna say, you could have them overlap by a week and open exam 5 next Monday and then have it close it for the that way there's a week between. Exam 5 closing and final week.
Got it. Okay. So it sounds like everybody wants at least the option of taking an exam 5. Okay, what in the world? I don't know. I think my arm decided to hit something.
If you want to just get rid of exam 5, I don't think anybody would.
Which
We could
also,
always-
it's just points to add up to the overall points.
You can just add the exam on the final.
Try this again. Wow, I don't know what it is about this room. It never does this.
Maybe give us a few more questions, or more tailored to 5 on the final. So it's kind of like 5 to 1.
To 1.
Like give us more, like on the number crunching columns, give us some more that are, kind of a little bit from the others, but more of them focused on 5 as well, so you can combine the 2. An option. If writing people ever work.
Oh, Jessica, it's only in here. It never has a problem anywhere else. Why, thank you.
So I thought we were doing starting chapter 10 today. Yeah, and it's chapter 9.
Yeah.
Sorry.
But the next one's really short.
Oh, chapter 10 short.
Mhm. Okay,
We'll finish it.
thermodynamics. That will be that one's very nice, especially if you like math. All right,
Will we finish that today or will it take all of it?
it'll take part of Thursday as well. All right, so let's do this. You still get the 2 weeks for exam 4. Let's open up exam 5. So they're going to overlap 1 week. So be very careful when you go in to take the test that you tell them which tests that you actually do want. So, all right, someone who has their calendar still open. So what is next Monday? Okay. Okay, and give me 2 weeks for that then. Okay, so if I still set,
What the heck?
and what is the last day before we go into finals?
The 2nd of December.
We don't want to open
But if you do a Monday to a Monday, it's 11:13 to 11:27. If you do a Monday to a Saturday, it's 11:25, but that's. what we do.
Not to mention we have to have time to get 5 exam back and so we can
Yeah.
make our corrections as well, if we want to, so.
So I'm thinking 11:13 to 11:27 for exam 5. That'll give me just enough time to get it back to you before finals. And then the
That was even worse.
So for exam 4, is that 7 and 8, and then 5 is 9 and 10?
9, 10, and 11.
11. Okay.
So the practice one that I was talking about, that is going to be on Canvas by the end of the week. Okay, I'll try and put it on tomorrow, but there's no promises, but it'll be by the end of the week.
That big one.
Mhm.
When does the required state one become open in?
So that'll be finals week. That one will be finals week. So it'll be over in the testing center the entire week of finals. So 12/2 to 12/8, something like that. Yeah.
We don't have classes for the days,
But we don't have classes any of those days.
and that's also when we take our Jolly one as well.
That's right. So there will be 2 finals in the testing center. There'll be a Jolly final and a standardized final. So you have to take the standardized, but you probably don't want that one to be your grade. So sometime set up a time to take the Jolly final as well.
And we have that quiz for the elements.
Oh, don't forget, yeah, the last portion of the elements, if you want to take that quiz, that one has to be in the testing center as well. Rows 6 on, I believe, is the rest, everything after 5. Okay, so there's our schedule for the rest of the semester. All right, let's talk reactions. Pretend I didn't go away from that. Is it because I'm sitting next to that thing? No.
Yes, it is, yeah.
Okay, let's practice what we learned about the metathesis reactions, and then we need to finish up oxidation reduction. So metathesis in the Jolly world, 1, just figure out what could happen.
No go.
Yeah, there was
No,
The other thing. Battery?
I think it's because I'm sitting next to, I think it's because I'm sitting next to that. Whoa. Okay, we'll just keep going because my screen does not look like that. All right, so for the metathesis, just do what could. Wow,
It's controlling.
that is, wow. What is wrong with you?
Everything. Haha.
Okay. Okay, let's try this for the whatever 6th time. Always figure out what could happen. Just swap partners. Just swap partners. And then we're going to worry about, will it happen? And that means check for a solid, a gas, a weak, or a non-electrolyte. That is one question. Okay, that is one question. A different question is then, can you write out the different reactions? And remember, the whole thing is the molecular. Then you can go to the ionic. And then you can go to the net ionic. Those are 2 completely different questions from each other. So we are going to try one for Brandon's sake. Okay, so this is one of his questions for his lab. So I have this wonderful solution of sodium chloride. Now notice I said solution. So the reason I put AQ by that is, what am I asking you to go grab off the shelf? Not a bottle of solid salt. I'm asking you to grab a bottle of salt solution. and I'm gonna combine that with some silver nitrate. And if this looks familiar to you, it's because you've done this in lab before. This is the identification of an unknown lab where you were making white precipitates, okay? But this is what you should have expected. What could happen? Let's just swap the partners. And I should get sodium nitrate plus silver chloride. You have to make the correct formulas. So sodium's a +1, nitrate's a -1, so it's balanced. Yes, Izzy.
This one's our molecular.
So this one is the molecular equation. So it is balanced as written. And then silver, I don't know what the silver is, so I'm gonna have to trust over here. And the silver on this side was linked with a nitrate, and so it was a +1. So it's linked with a -1 on the right, so it's correct as written. Okay, and then I balance the whole thing. This is what could happen, and it's balanced. Will it happen? I'm looking for solids, gases, weak, or non-electrolytes. And now, my first question, is that ionic or is it molecular? It's ionic. So the only thing it could do is float around or be a solid. How would you tell me whether it would be a solid, whether it would be a precipitate? You'd go to your solubility rules. And your solubility rule says all sodiums, all alkali metals are soluble. End of state. And for alkali metals, there's no even excepts. It's 100%. And the fun thing is, nitrates are the same way. All nitrates are 100%, which means you didn't make a solid. It is just floating around as ions. All right. Next question, is that ionic or is it molecular? It's ionic. So the only option is either it's going to form a precipitate, a solid, or it's just going to be floating around. And the way you would answer that is to go to your solubility rules, and there are no ionic gases. Yeah. Naturally. Natural ionic gases. Yeah. Yeah. Anything hot enough, yeah. So it's ionic. So all chlorides are soluble, except, is this one of your accepts?
Yes.
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 So if it's an accept to its solubility, it's going to make a solid. So will this reaction occur? The answer is yes. You should see a solid being formed. Okay, we just answered that question. Yes, it should happen. The next question is, okay, what's really happening? Who's really involved? Who's really involved? We're going to try and get to the net ionic. So the molecular equation is just everything balanced. So this one's the molecular. The ionic equation tells you who's floating around as ions, okay? And I'm looking at the pink page on your reference sheet. And so the question you ask is, first, is it aqueous? Yes. Is it ionic? Yes. Break it up, which means it's floating around as ions. So this one, look at the black, is really a sodium ion and a chloride ion. You're literally telling me what's floating around. So when you grab that bottle in the stockroom, you actually grabbed a bottle of sodium ions and chloride ions. That's telling you what you grabbed. Yes. All right. The next one. Is it aqueous? Is it ionic? Break it up. So really what you grabbed was a bottle that had silver ions floating around and nitrate ions floating around. All right. What did you create? Is it aqueous? Yes. What does that mean? It means they're not stuck together. It's floating around as sodium ions and nitrate ions. The last one, is it aqueous? Leave it alone. Okay, what really is in that beaker, test tube, whatever? It's a solid. Doesn't tell you what color, but it does tell you there's a solid. So the ionic equation tells you what is actually floating around, what's in your solution, what's in your container, okay? Your net ionic tells you who's important, okay? So it gets rid of all the spectators. All right, well, and it has to be identical. I have a sodium ion that's aqueous on the left, and I have a sodium ion that's aqueous on the right. So is the sodium ion really doing anything? No. I have a chloride ion on the left, but I have silver chloride solid on the right. Should I get rid of it? No, because they're not identical. I have a silver ion on the left, and I have silver chloride on the right. Nope, I better keep it. I have a nitrate ion floating around on the left, and I also have a nitrate ion on the right. So I'm going to get rid of those. So in the end, what's really happening is some chloride ion is reacting with the silver ion to make silver chloride. And that is what the net ion is trying to tell me. Okay. Yes. Correct. Mm-hmm. That is an amazing question. So if you were to go look at the solutions on the shelf, not all of those chemicals like to be dissolved in water. So with time, they will precipitate out. They are not homogeneous solutions. So before I let you use them, I either have to heat them up and get them homogeneous again or shake them. I have to get them homogeneous again. Yes, that's exactly it. Mm-hmm. All right, let's try one more metathesis. All right, so we did a solid. You know what? You designed the metathesis. I want to make a gas. What 4 gases are available to me? What 4 gases can I make? Okay, thank you. I'm loving that. But in the metathesis world, there's 4 and they're listed on page 5. You can make carbon dioxide in water. You can make sulfur dioxide in water. You can make ammonia in water, or you could make H2S. Okay, dihydrogen sulfide. All right, so those are the 4 that you could make. So let's work backwards. What do I have to put together? Cleave them in half. So that on page 5, there is 4 gases that you need to keep. Oh, sorry, not on the reference sheet. Sorry, in the notes. Oh, sorry, page 6. Sorry, page 6. Oh, absolutely. You can write them on reference sheet. Mm-hmm. So let's work backwards and let's figure out how you could make it. So remember, this is the product. So you have to cleave them in half. So if you wanted to make this one, tell me the 2 pieces that you have to add together. If you wanted to make H2CO3, you had to start with an H, which is an acid. All right, give me an acid. I don't care which one. Okay. So that part is my carbonate. H, I could use water. I could use HCl. I could use HB or DC as long as it's an acid. I don't care which one it is. So I will just use a strong acid. All right, because I need this piece to go with that piece. And then I don't care what those 2 do. Okay, but that's the pieces that I want. All right, what do you want me to grab off the shelf? Do you want me to grab a bottle of solid sodium carbonate? Or do you want me to grab a solution that's already been made? Solution. Oh, thank you. Now that's another layer to the question. Which would give me the better yield? Which would take the shorter time? That's a Chem 112 question. So for us, no easy, just choice. All right, swap your partners. The H goes with the CO3. and the Na goes with the Cl. You have to put the subscripts, you have to make the correct formulas. And so HCO3 is not valid because CO3 is a -2. So how many hydrogens do you need to make it neutral? You need 2. I remember a redox changes identity. So a sodium ion is still a sodium ion on both sides. Yes, because I didn't change it from Cl to Cl gas. Yeah. Oh, you're allowed to react. So switching partner just means you're allowed to react with your pieces. But are you changing identity? So a hydrogen is still a hydrogen, but it's not H subscript 2. It's not hydrogen gas. It didn't change identity. It's still part of somebody else's formula. Ah, but that's not hydrogen gas. It's still just hydrogen connected to another piece. Okay. So yeah, so let's keep going, but we'll do the redox. It'll actually make more sense when I go through the redox. Yes, that. Oh yeah, no, we're just not there yet. Yeah. So now we're looking at the sodium chloride. So the sodium's a +1, the chlorine is a -1. So that is balanced as is. Don't touch the subscripts again. Now let's balance the overall. And we'll put a 2 here and we'll put a 2 there. Okay. That's what could happen. Will it? That means put the phase labels. H2CO3, is it molecular or is it ionic? It's molecular. Immediately put AQ. Okay, if it is ever molecular, immediately put AQ and then do the check. Is it one of the 4 you're supposed to recognize as gases? Ah, so then it's probably better to rewrite it as what it really is. That is really H2O, and you could put liquid or aqueous, it doesn't matter, plus carbon dioxide gas. All right, is sodium chloride molecular or ionic? It's ionic. So is it floating around or is it going to make a solid? It'd be floating around, so AQ. And there's your answer. Did you create a solid, a gas, a weaker non-electrolyte? And the answer is yes. I created a gas, but I also created a weak electrolyte as well. So will this reaction likely happen? And the answer is yes. All right, let's do another one. I really, really want to make some magnesium sulfate. Okay, I want to design an entire lab around making magnesium sulfate. Can you design that for me? What are you going to add together? Okay, so are you seeing we're just going to split the 2? If we're going to do a metathesis, I need to have something attached to a magnesium and its other partner attached to a sulfate, okay? Now you just have to decide, what do you want them to be? Do you want to just use what's available on the shelf? Do you want to order something? What are my limitations? And right now it would have to be something on the shelf, but, and thank you for saying magnesium oxide, because it's always faster if they're in solution. They're always faster in their solution. So let's say I went and grabbed some magnesium oxide. How easy is that to make a solution? I'm asking you if it's soluble or not. All oxides are insoluble except, okay, so that's going to take you some doing to make that into a solution. So is that what you want to grab off the shelf or do you want to grab something else? All right. What is soluble with magnesium? pretty much everything above nitrates, acetates. Are you seeing on my solubility rules? I'm looking for something that's soluble with magnesium. Does not matter which one I grab. How about some nitrate? How come I grab nitrate? Everything soluble in nitrate. It's gonna dissolve really easily. Okay, so do you want to just grab it solid or do you want to take the effort to make it the solution? Okay. All right, I need some kind of a sulfate donor. What do you want? Who would be the easiest that's 100% soluble? Rubidium, okay. How come rubidium? Because it's an alkali metal and all alkali metals are soluble. Oh, but rubidium is a +1, so what's my subscript? All right, do you want to go to the effort of making the solution or do you want me just to grab the solid off the shelf? Let's grab the solid this time. At least one of them has to be aqueous or you have to add the water. Does that make sense? You do passage. All right, that's what I added. What could happen? Just swap the partners. And I'm going to make magnesium sulfate. All right, magnesium's a +2, sulfate's a -2, so that's correct as written. And rubidium nitrate. Rubidium's a +1, nitrate's a -1, so that is correct as written. And then I'm going to balance out here. Okay, that should be my balanced equation. That's what could happen. Will it? What am I asking you to find? Okay, let's do phase labels. Is this magnetic? Is this molecular or ionic? It's ionic. So is it floating around in solution or is it a solid? So all sulfates are soluble, except, is magnesium one of my excepts? Oh. Okay, it's floating around. How about rubidium nitrate? Is it molecular or is it ionic? So it's soluble because of the nitrate. What? Okay, let's ask it. Did anything happen? And the answer is no reaction happened. That's your molecular equation. Let's look at the ionic equation. Is it aqueous? Yes. Is it ionic? Break it up. Okay, I cannot stress this enough. That 2 means there's 2 nitrates. Okay, so 2 nitrates. Yes. No, because it didn't react with it. It was just dissolving in it. Mhm. Yeah, it's just dissolving, so you don't have to balance it. All right, is the next one aqueous? Leave it alone. Is the next one aqueous? Is it ionic? Break it up. Is it aqueous? Oh, sorry, the next one, yes. Is it ionic? Break it up. Okay, now remember, there's 2 of them. So I'm going to put a 2 rubidiums right there. I'm sorry, I write too big, so this will have to go underneath. 2 nitrates. All right, that's what's floating around in your solution. What's really happening? All right, we're looking for the net ionic. All right, I have a aqueous magnesium on the left, and I have an aqueous magnesium on the right. I have 2 aqueous nitrates on the left, and I have 2 aqueous nitrates on the right. I have a rubidium sulfate solid on the left, but I have rubidium and sulfates on the right, so those don't cancel out. So what's really happening here, no surprise, does anybody recognize that equation? Starts with a D. It's the dissolving. This is the dissociation equation. No reaction happened, but look what it's telling me. Hey, idiot, all you did was dissolve the rubidium sulfate. That is all that happened. Did a reaction happen? No, but I did dissolve the rubidium sulfate. That is super cool. It literally tells me what is happening. Uh-huh. But you could tell me it dissolved. Okay, but dissolving is not a reaction. That's a physical change. That's a physical change. Oh, huh. How interesting is that? Do you see how we can take this one step deeper? And now I could tell you how much you started with, and you could tell me the theoretical yield and how much you should be able to make. And then you could go do this in lab and find your own actual yield. Now we're to Kendra's lab. And you could say, oh, I was supposed to get 35 grams and I only got 2. That's where you go, oops, better do that one again. But if it happens 3 times in a row, there's something. Okay, are you seeing this is just the prediction? You already know how to do the math. You already know how to do the math. Okay. All right, now let's go to our oxidation reduction reactions. Okay. Clear this out. Sorry, I just want to make sure it was still recording. All right, when we're talking about oxidation and reduction reactions, they're not going to keep their, if you will, identities. They're going to change into something completely new. So if you started with sodium ion, it's going to go to sodium solid. Or if you started with a solid, it's like metal, you would go to the metal ion. Okay, but it's going to change identity. And oxidation is the loss of electrons, where reduction is the gain of electrons. And the wonderful little mantra I use still to this day is Leo the lion says grr. Loss of electrons oxidation, gain electrons reduction. Or there's oil rig.
I like that one.
Oxidation is loss, reduction is gain. Okay, so whichever one you would like. That's just a nice little mantra to kind of keep it straight. All right, I'm literally talking about transferring electrons. You cannot have one without the other. They always occur together. Okay, electrons are not going to pop out, float around in solution, and then find somebody to react with. Okay, the electrons have to go from atom to atom. They're not ever floating around. But I can write something called a half reaction, which I'll show you in just a minute. But I'm going to just put one up here, and you're going to tell me whether it is an oxidation or a metathesis based on our definition. So let's take, it's cold outside. So let's take some methane, some natural gas, and let's burn that in the presence of oxygen to make some water plus some CO2 gas. And let me see, balance this thing out. So let me see, I have 2, 3, so let's put a 2 there. So there's a, okay, 1, 2, 3, 4, okay. Now keep in mind, I came up with that equation, you didn't, but can you tell me anything similar? Do you notice those are not ionic compounds? Okay, so number one, they're not ionic. We've always kind of played with most of the ionic. So this is your question. Most of our metathesis uses ionics. Not all of them, but most of them. Do you see this is literally going from oxygen gas in nature to water and carbon dioxide? Is it oxygen gas anymore? It changed identity. This must be a redox reaction. Okay. How about this one? I went from a compound called methane gas with a carbon to a compound called carbon dioxide gas with 2 oxygens. Did that change identities? Okay, now that one's harder. Well, didn't I just swap the carbon with the hydrogen and the oxygen? There's the key. There's the key. Did I just swap or did I change identity? And I'm changing identity. And if you can't tell, let's try the math. Like, oh, I'm not sure. I'm not sure if you changed identity. So let's check. All right. So we have to have an oxidation number for every atom. And just as a reminder, if it's elemental, the oxidation number is 0. If it's monoatomic ion, it's the same as its ionic charge. You may trust all of the alkali metals and the alkali earths, and you may trust fluorine to be a -1, and you can trust hydrogen to be a +1, except in hydrides. And you can trust oxygen to be a -2, except in peroxides. All right. So, oh, sorry, the alkali earth and the alkali earth, sorry, the alkali metals and the alkali earth. You can trust them to be +1 and +2. All right, so let's go up to that CH4. You got to trust somebody. Who are you going to trust? We're going to trust the hydrogen. And the hydrogen is going to be a +1 unless it's in an ionic species called a hydride. Is that an ionic compound? No, then that's not a hydride. So I'm going to trust the hydrogen to be a +1. Now there's 4 of them. Each of them is only a +1, but there's 4 of them. So what does that make carbon? A -4. If you want to do the algebra out, what you would do is carbon plus 4 hydrogens is equal to, it's a neutral species, so it would be 0. So the carbon plus 4, and each hydrogen's a +1. So the carbon is a -4. So if you wanted to do it in algebra form, okay, that's what we just did. So really that's the most common. That's hydrogen peroxide. All the others will have peroxide in the name. All right. I have 2 down. I have to do them all. How about oxygen gas? Where does it fall in my oxidation number rules? Is that how oxygen occurs in nature? Diatomic as a gas, they both have to match. So is that how it occurs in nature? Then it's 0. Elemental. That's how oxygen occurs in its elemental state. All right, let's jump over to water. Who are you going to trust? In this case, just choose one. If we trust hydrogen to be a +1, there's 2 of them. So what does that make oxygen? -2, which is what we expected anyway. All right, let's go over to carbon dioxide. Who are you going to trust? And it's a -2. but there's two of them. So carbon is a +4. Did any of them change? Yep. And remember, you can't have just one change. Oh, so carbon went from a -4 to a +4. Oh man, what's direction is that? I went from negative towards positive. And remember, electrons are negative. So if you gain electrons, you become negative. If you lose electrons, you become more positive. So what am I doing right there? I'm losing them. So this is oxidation. Okay, that was a funny way of saying that. Does everybody get it? Electrons are negative. So if you gain them, you're going to become more negative. If you lose them, you're going to become more positive. And I went from a -4 to a +4, so I'm becoming more positive. So I oxidized. How many electrons did I oxidize? Remember, I went from, think number line, I went from a -4 to 0. And then I went from 0 to a 4. That's 8 electrons. Whoa. That carbon lost 8 electrons. And remember, I told you the more it plays with, the more energy there are. Okay, this is what runs your furnace. This is what heats your house. It puts out a lot of energy. That's a lot of electrons. Okay, how about hydrogen? Hydrogen on the left is a +1 and hydrogen on the right is a +1. Did it change? No. Oxygen on the left is 0. And on the right, in both cases, it's a -2. So first of all, was it reduced or was it oxidized? It was reduced because it became more negative. And how many electrons was it playing with? So each oxygen is playing with 2 electrons. Each carbon is playing with 8 electrons. You can't have an odd pair out. So how many oxygens are you going to need to counteract 1 carbon? Thank you. Are you seeing 4? So diatomic oxygen, there's 2 of them, but then you have to have 2 of those. So 4 oxygens will gain 8 electrons where 1 carbon will lose 8 electrons, but they have to match. So 4 oxygens have to occur for every 1 carbon because each carbon is playing with 8 electrons. So those oxygens better supply 8 electrons and you're going to need 4 of them. You're going to need 4 of them. So my reaction is playing with a total of 8 electrons. All right, let me go back to the did it change identity issue? Did it change oxidation state? When I say identity, I'm actually asking oxidation state. Did it change oxidation state? Yes, then this is a redox reaction. Okay. Really quickly, I'm going to write that last equation that we had. Let me see, we did HCl. I can't remember what we did, plus sodium carbonate. All right, let's check this one. Hey, my phone's in here. I thought I left it in the lab. All right. Yeah, I really know where my phone is at all times. All right, on the left, HCl. Who can I trust? Which makes the chlorine. All right, sodium. Oh, I can trust sodium because it's an alkali. So it's a +1. Oh, I have to do the carbon and the hot. Okay, do you see? I'm not looking for the ionic. I'm looking for the oxidation number. So what I really need to know is each one of those. So who am I going to trust? The oxygen. So 1 carbon plus 3 oxygens, and each oxygen is a -2. But do you notice the way I wrote it here? Is that species charge? Yes. Okay, so my carbon minus 6 is equal to a minus 2, so this carbon is a plus 4. Okay. All right, let's say you didn't break it up first. How would I have written it? Yes. Oh, now remember, those don't take into account how many of them there are. Each sodium's a +1, each carbon's a +4, and each oxygen is a -2. I have 2 sodiums and I have 3 oxygens. Okay, so to Izzy's question, if I didn't break it up like that, I could have broken it up like this. I have 2 sodiums, I have 1 carbon, and I have 3 oxygens, and that whole species is neutral. Okay, because the sodiums are still attached to it. In this case, I have to be able to trust 2. So which 2 am I going to trust? Each sodium's a +1. I can't trust the carbon, but I can trust the oxygen. And guess what? You'll get the same answer. You'll get the same answer. Okay? So whichever way you want to look at it. Ooh, how about water? Who are you going to trust? Water never changes. It's a +1 and a -2. How about carbon dioxide? And there's 2 of them, so what does that make the carbon? And last but not least, who are you going to trust? Which makes the chlorine A. Did anybody change? That's a metathesis reaction. Hopefully that gave a different ritual. Okay, so nobody changed oxidation state, that's a metathesis. You change oxidation state, that's a redox reaction. Okay. There are more, but you don't see them until organic chemistry. This is pretty much what you get. Most pieces of metathesis are ionic. Do you notice this one has a molecule in it? Yeah. Sodium carbonate. Mhm. So you can't just base on that for metathesis. Okay. Guess what? There's, you know, we need to do another one. Okay, it's harder to make up redox reaction. Thermite. Okay, so we need aluminum solid plus oxygen gas. Right, aluminum oxide, right? Thermite? No. Is it zinc? It's iron oxide. Iron solid plus oxygen gas makes Fe2, let me see, Fe2O3 solid. I believe that's thermite. All right. Somebody Google what's thermite.
I don't know about that message.
There has to be water. So what is its final? Yes? All right, so there. Boop. There's thermite. Okay, and we do have to balance it here. Let's see. I have 2 aluminums, so we'll put 2 aluminums. I have 2 irons, so we'll put 2 irons, but my oxygens are gonna be, oh. Okay, well, that balanced quite nicely. Okay. Can you tell me who's changing and whether it's metathesis or whether it's redox? The key here is, you see, I went from aluminum solid to iron solid. Oh, I definitely changed identity. But let's check. Aluminum solid, is that how it occurs in nature? So its oxidation number is 0. Ooh, who am I gonna trust? Who am I gonna trust? Oh, actually. Actually, yes, they will. They will. All right. If I have oxygen at a -2 oxidation state, what in the world does that make that iron? Let's check. 2 irons plus 3 -2s is equal to 0 because that whole thing is neutral. So 2 irons equals a +6. So iron is equal to a +3. Okay. All right, so over here, the oxygen is also a -2. So what does that make the aluminum? +3. And iron solid, that's how it occurs in nature. So that's 0. All right, my aluminum went from a 0 to a +3. Was that oxidized or was that reduced? Okay, so did I become more negative or more positive?
Oh,
Oh, sorry, yeah, no.
I see, but
Oh, no, we're good. So it was oxidized because it became more positive. Okay, now when I say that, it doesn't have to be positive. It became more positive. So if I went from a -7 to a -3, it's still negative, but it became more positive. Okay. All right. So let me see. How about the iron? It went from +3 to a 0. So it was reduced. How many electrons is the aluminum playing with? How many is the iron playing with? Do they match? Okay, then we're okay. The whole reaction is playing with 3 electrons, and it was a redox because we changed identities. We changed identities. Is an oxidation number change. Yes, just. Oh, thank you. So to be balanced, it's playing with 3. To start with these species, it has to do it twice. It does the reaction twice. Twice, correct, correct. Yes, yes. Mhm. Oh, all right, thermite. Hey, is everybody seeing that we could have done this? No, we are not. We're not doing it in lab. We did something just like this, did we not? We took copper oxide and we put it in the presence of zinc and we reduced them back to copper metal. We did this same reaction, only I chose ones that weren't going to blow up in your face. Literally, yeah, wasn't that nice? We could do this in the lab easily. We could take a little aluminum solid, which we have, and we have iron oxide, it's just rust, and we could mix them together in the solid form and heat it just a little bit. Okay, and again, in Chem 112, we'll learn that you do have to give it a little boost. It's called an activation energy. You have to give it a little boost. Once you give it the boost, well, then you make something a little bit more reactive than what we like about it. Mostly.
Enough that like I could take that. So, you know, this is my first time, put it together and do the rest of it.
Yes, you could.
Wow. that's
Yes, you could.
amazing.
The world looks very different after this class.
I've got plenty of rest, plenty of aluminum foil.
In fact, you'll go look under your kitchen sink or your bathroom sink and you'll be like, I don't think I should be storing those two things next to each other. Whoa, okay. You laugh, and yet, let me show you.
You don't give us anything left, it's combustible, I heard.
I try and give you combinations that only are fairly safe,
I should give this warning.
I just don't want to mix it.
Yeah.
I don't want to mix something together or you have it reopened for a big room.
Yes, you did.
How so?
Oh, no, and it's easy. And I have a terrible story for you. So let me show you what you did. So this is ammonia, okay, or ammonium hydroxide, aqueous, okay? So this is Windex, okay, the main component of Windex. Or you can literally buy ammonia, okay, NH3 or NH4OH. Well, this happens to be bleach. Hypochlorous acid. So you took some Windex and you took some bleach, or guess what? Comet, the Comet powder has chlorine gas or chlorine in it as well. So it could have also been, you know, Comet. And so you're cleaning your sink. Yeah. And so you're cleaning your sink and you have that wonderful sticky powder, you know, in your sink, and then you sprayed the mirror. And the mirror dripped down into the sink. And guess what you did? You literally made chlorine gas. And by the time you can see it and you can smell it, you've already received a nasty dose. It's green. It's green. But by the time you can actually see green, that's really bad. That's really, really bad. And yet what is underneath your kitchen sinks or your bathroom sinks? And then what did everybody do?
That's kind of like how to do projects on, it's like, hey kids, study
What? Can I try it? But no, that is a very simple thing. And I know better. I know better. And we have a rule in our house, and have always had a rule in our house, that you use one cleaner until you're done and it's washed away before you use another cleaner. And my no mixing. And they were, my kids were always like, what, Mom? No.
My
Okay.
dad's always mixing things materials together, pretty strong.
To make strong, and that works sometimes too. That, yeah. Let me see. I think I actually don't remember it off the top of my head, but you do make some nitrogen gas, which is no big deal. But then I think you also just make a caustic HCl. Yes. Right, and so it makes a lot of multiple products as well as the chlorine. It's not simple, there's lots of them. But the chlorine is the nasty one. So during my fun chemistry shows, I really like to do one that uses acids and bases because they turn colors. So I take some vinegar and I take some cabbage juice, and when you put red cabbage juice and vinegar, it turns pink. You know, oh, and I didn't want pink Kool-Aid. And so then I pour it in baking soda and it turns fizzy and it turns purple. Well, I didn't want grape soda. So, and then I have all of these combinations and it changes colors. And all you have to do is vary the strength of acids and bases. But I really wanted green. And guess what color green is? Uh-huh. What was I I don't know what I was thinking. Oh, man, yes, I did. So I have all of these cups sitting there. And my last one is I have some ammonia. Oh, and it turns the greatest green in the whole world. It's just this brilliant green. So proud of myself. Ooh, it's lemon lime. But then I always end with, oh, but I didn't want anything sugary. I just wanted water. How do you get rid of the color? You put it in bleach. My last cup is always bleach. No matter what I start with, my last cup is always bleach. So I'm blah, blah, blah. And the moment I dumped, I realized, and I was like, I just poisoned a second grade class. It starts, it starts fizzing. Oh, no, even better. Okay, so this was a spring show. It was a spring show. I'm not joking. I wish I had it on video. So here I am, a friend, blah, 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 and I went. And it also really likes to water flowers. And I ran to the window and I out the window. And the kids thought it was part of the show. I was like, and then you can also water the flowers. Chuck clear out the window. And the teacher was like,
Did you tell me why?
no. It was
So really, you just, it'll never been.
I mean, it was like 2 seconds by the time I combined it. So it had just barely started bubbling. So, but I shoved that cup out the window. She's like, why are you throwing your cup out the window? But okay, the color of the original ammonia solution is my nice lime green right there. But if you see this color of green bubbling out of that container, you poisoned yourself. Yeah, and you can it gives you quite the headache, gives you stomach ache, and then you destroyed brain cells. Yeah, no coming back from that. Don't do that. Don't do that with second grade. See, it was your cleaning solutions. Oh, and it definitely burns you because it gets better. Oh, it gets better. Yeah.
Yeah.
Because urine has the nitrogen in it. That is exactly. Okay, not that you ever do this, you put the cleaner in the toilet and then leave it because you want it to, leach later, and then your children come along and use the toilet without flushing it. Oh yeah, it changes color. Oh yeah. Oh yeah, it changes colors. Different variation with a different oxidation number. You don't have to be worried about that one. You don't have to be worried. But let's say the chlorine gas didn't just, absorb through your skin and then settle in your fat cells and stay there forever, which is, the problem. You breathe it in and your lungs are full of water, and you have now created what inside your lungs?
Uh-oh.
And it does the same thing on the skin.
And it does the same thing on your skin
Oh, you're.
and your eyes.
Have you ever realized that?
Uh-huh. Mhm. It also is a very viscous solution. But yeah, you're denaturing your protein.
You're in for a world of pain now.
Yeah. Oh, there's the $1 million question. Why do I do that? Okay, the chlorine in tools is supposed to be that. But how do they get the chlorine? Has anybody worked at a pool, by the way? Okay. Oh, Megan did. Yes. Do you remember which kind they? Okay. We're gonna have to ask my Olympic. All right, so some pools, if they're larger, have a tank of chlorine gas literally on the premises, and they bubble chlorine gas through the water, which then goes out to HCl, and then there's so much water that it goes out to the chloride ion. Somebody better be very smart if they're the ones controlling the amount of chlorine gas going into the pool. Okay, so that's really big swimming pools that, you know, can afford that and they can, you know, have somebody that will take care of it. That's Olympics. The other ones, sodium hypochlorite is the bleach that you can buy off the shelf. They have great big bleach containers that they dump in, and then somebody just has to be able to regulate the limiting reagent equation so that they know how much bleach to dump in to change. Because remember, you can't have too many chlorines in there. Other words, have you ever swam in a pool with too much chlorine? It literally, you get chlorine poisoning. It absorbs through your skin. It makes you, it's terrible, right? So you can either use chlorine gas, you can use sodium hypochlorite, or you can start with hypochlorous acid. Or a magnesium salt for those small pools that we don't want to kill everybody in the vicinity. And then there's variations on the thing. Yes, that is one of the byproducts. And the thing with these equations is there's not just one type of product. It's not a simple, just you make one or two things. Yeah, it's a combination too. Thank you. And you should not be able to, because it's all been converted to the chloride ion or to these harmless variations. But what if they put too much in? Although the urine doesn't contain a very high quantity, so pretty minimal problem there. All right, another fun, stupid story. So my kids always took swimming lessons in Shelley, and we have a really small pool. And pretty much the lifeguards are the ones that have to keep the pH levels and the levels of the pool. And it is not an easy thing. So if anybody has had to like test pHs and stuff with any type of a water system, like even aquariums, it is not an easy thing. Well, when you know nothing about the chemistry, it's even harder. So we were in there and the pool had been closed because, you know, and they have to test for microorganisms and then they have to treat it and blah, blah, blah. It had been closed. So they had to put more chlorine in the water to purify it. But they couldn't get the numbers right and the pool it wasn't coming out right. But they were losing money on their swimming lessons. So if it fell right in the safe category, they'd open up their swimming lessons. And so my kids were in the swimming pool and I was sitting next to the office and they're having this huge discussion about how much hypochlorous acid, and they didn't call it hypochlorous acid, by the way, how much stuff they should dump into the pool to change the pH so that they killed all the microorganisms. They had no idea what they were talking about. And they had a paper. Does anybody understand which one? Well, we tried this step. I'm like, oh my gosh, I'm gonna go get my children out of this pool. But yeah, it's just a recipe and it says, take this water sample and if this thing turns pink, go add this much. They have no idea why they're doing it. Oh no, I bypassed the pink to the purple. So you jump to step 12 or you jump to step 12. If you overshoot, immediately add sodium hydroxide to neutralize. And I'm like, oh my gosh. But
So like teaching lesson, like do this and this, like you want to get
I almost did. If it wouldn't have just caused more problems. And I thought, you know, but that's like how much science is going on out there that nobody knows anything and you're walking right through it. All the time. But that was a doozy. I actually did, because I listened long enough that the concentrations they're allowed to play with aren't dangerous enough to, yeah. Like, what kind of ppms are you playing with right there? So I eavesdropped long enough to. If I had thought there was a problem, I would have made them evacuate the pool, but that would have just made, me brownie points.
Brownie points.
Yeah, this person came and told all the people to get out of the pool, and yeah, that would have made me a very popular person in showing, but. Well, actually, to half the people it would. The others would have just been mad. Thank you for getting our kids out of the chlorine pool, but what's chlorine? All right. I felt so bad for those kids. They were like 16 and 17-year-old kids that were, the lifeguards and the.
I don't know if this was, what you said was everybody. Back when I was in, grade school, I had this one classmate who said about, when swimming in a pool so long, you got chlorine poisoning.
Uh-huh.
But actually,
That's a real thing. Uh-huh. So, your first sign is your hair bleaches out. Okay, anybody who's been a lifeguard, your hair bleaches out because eventually just that concentration will bleach your hair. And then your swimming suit will start to bleach. And then it's really bad. When your swimming suit changes consistency, does everybody know what I'm talking about? Yep, you're actually eating your swimming suit. And then you go crunch, crunch, crunch. Uh-huh, uh-huh. And then once you get past that level, it absorbs into your skin. Yeah,
so your swimsuit becomes crunchy.
it actually becomes crunchy. Has anybody had that wonderful other than, okay. Now with time, it'll happen anyway, just with age, but
Yeah, he said he got chlorine poisoning.
yep, it's a real thing. All right. See, look at me go off on my little tangents. All right, that, I'm just gonna pull up that chapter to make sure we're finished with it. Okay. It's close, it's close. All right. Actually. All right, so we have talked about our acids and bases and our different reactions. So there were the four, okay? And then we did the electrochemistry. And so electrochemistry is literally converting, chemicals into electricity. All right, they always occur together. Oxidation is loss, reduction is gaining. This is just a term that you're going to hear. Okay, anything that is oxidized is called the reducing agent. Why do we always have 2 or 3 names for everything? But if you're oxidized, what are you forcing your partner to do? Be reduced. So the thing that's oxidized is also called the reducing agent. Yes. That is exactly how batteries work. Exactly how batteries work.
Wait a minute, how do they work?
So it's a redox reaction. In fact, they're very simple redox reactions. And so my witch potato that's out there, I'll actually show you the reaction that's happening for the witch potato in just a second. It's easy to make batteries. Okay, you are so young, but Gilligan's Island. Thank you. And they take the coconut shells and the salt water and they're beating it. Yeah, they actually are making electricity, not enough for what they were doing, but you can create electricity. It's just electronics. Yeah, it's very simple.
It's oxidation reaction, but also batteries as well, like one
Yep. Yep, that's exactly. So electrochemistry is still a huge area.
You know, when experiment we did in I wrote that becoming like it's like electricity that maybe showed how that how much your body had what you actually inside it. So they wrapped a wire around a light bulb and they had nothing else in it except for his hands. And after enough hands grabbed the whole wire, the light bulb turned on. It was feeding off the electricity from the bodies.
Oh man.
That was cool.
Yes, absolutely. You are a great big redox reaction happening, like literally, yeah, right there. So, so we've got, so your body is very conductive and it also creates. The little Pigeon chicken, it has the two electrodes at the bottom of your body.
Reacts.
Actually, yeah. All right, so here is an example of an oxidation. This one went from 0 + 1 to a +2 to 0. So if we change oxidation numbers, we have done a redox reaction. And then I mentioned something called a half reaction. That's nothing special. It's just looking at the pieces individually. So the zinc went to zinc ion +2 electrons. And remember, that's a product, so it lost it. And the 2 protons picked up those 2 electrons to make hydrogen, so it gained it. And so that's just called a half reaction. It's a visual. Okay, they don't actually occur that way. It was just a visual. Okay. And then we talked about the oxidation numbers and then how to figure those out. And so the last thing is, what are some common ones? Like what are these batteries called? These are all redox reactions, but then we have names for them. So if you took a high school chemistry class and you memorize these names, it's not because they're different. It's just you're trying to narrow the different types. All right, so combination, you combine 2 things to make something else. Woo! You combine sodium solid and chlorine gas to make sodium chloride. Okay, so that's called a combination redox reaction. Or iron plus oxygen to make rust is technically a combination redox reaction. You can actually decompose things. So you take one thing and break it back up to its parts. So carbon dioxide can be decomposed into elemental carbon and oxygen gas. Again, it's just a redox reaction, but technically you're decomposing it. Aha. There are displacement reactions, but this is not metathesis because they're changing oxidation numbers. Okay, so I'm going from zinc solid to zinc +2, but they're changing places, if you will. One's going from neutral or 0 and becoming ionic. And then the example that I used was combustion, burning in the presence of oxygen gas to make carbon dioxide and water. Carbon dioxide and water. So the one that we did in lab, I'll just put it up here. Did we use copper too? Yeah. In one class.
So what?
So you're going to start predicting these reactions. So right now I have to give you the whole equation. In Chem 112, you'll be able to predict the products. All right, so we took copper oxide and we reacted it with HCl, and we came out with this wonderful blue, solution, and then you threw zinc in there. And we ended up with zinc chloride. That was a redox reaction because we went from copper and its ionic state of +2 to what? Copper with an ionic or an oxidation state of. And we took the zinc, which was 0, and now what is it? Zinc +2. And also we went from hydrogen +1 to hydrogen 0. You can oxidize and reduce more than one thing, but they have to always balance. Yes. Oh, so the oxidation. So the zinc used to be metal and now it's ionic, the state of it. Yeah. And my wonderful witch potato out there is doing this. Mhm. If you look in my wonderful witch potato, there's 2 little electrodes. One is copper coated and one is zinc coated. The potato has nothing to do with it except an aqueous environment. And so it will eat the metal off of one and convert it to the ion, and it will coat out on the other electrode. That's all my little rich potato is. And guess what? Yep. Yep, that's exactly it. That's exactly what they do. Yeah, it's easily done. Just go and run it. Yes. Yes. Keep in mind, when we say heat, heat could mean at -2. That could be enough heat for that reaction. Where for combustion, it's quite a bit harder than that. Every reaction requires a little bit of, it's called activation energy. Every reaction has a different amount. Yeah. Yeah. Right.
So for combustion, isooctane where random
Mhm. And you have to supply the spark. So the spark plugs. That is exactly it. That an internal combustion engine. Yeah, that's exactly it. And so your activation energy comes from the spark. Yeah, exactly it. That's the next chapter. All right, and then. Okay, and this is what's on your reference sheet. So here's my little summary, and there's a variation on your reference sheet. Okay. Correct. Mhm. Yep. Yep. You go to the other one. All right. Next, where are you? Next chapter 10. Thermodynamics. All right, you are either gonna love this or it's just math. Okay, it's basically the same type of chapter as our gas law chapter. There's not a lot of meat to it. It's a whole bunch of math. It's a whole bunch of math. All right, so I'm gonna talk about what thermodynamics means. Thermodynamics makes the world go round. Okay, thermodynamics means energy. Everything has to have some kind of energy. Thermochemistry, I'm going to show you how that applies to the chemistry world. Enthalpy is one type of energy. We're going to do some measuring heats of reactions. This is a really good one, by the way, for your independent project. When we get done with this chapter, you might go, ooh, that would have been a fun one. Okay, so if this kind of strikes your fancy, I can help you design one around this topic. Yeah. Yes. Exactly. Okay, sorry, you may not make mustard gas.
Our measurements will be, people in the library start talking about it.
That's one way to look.
Thank you.
Way to get results.
How are you going to quantify that? Well, how many people go to the hospital? Yeah. We just won't come.
Yeah.
All right,
I'll just call it a
just call in sick that way. And this has one handout. Or spring gas panels, yeah. Okay, so 8, yes, I believe. Oh, because we did, there might only be 17. When we get to the end, I'll make sure that, okay, here's all the ones that are required. Right, so thermodynamics is basically the study of energy, and end of statement. Everything requires some kind of energy. So the study of the laws that govern the energy and the entropy changes of physical and chemical events. Okay, entropy doesn't mean anything to you right now, so if you will, just think energy. Thermochemistry is the study of the energy changes specifically of chemical reactions. Okay, so it's a subset. All right. If you took a physics class, this is a complete review, but energy, there's two types of energy. There is potential energy and there is kinetic energy. Kinetic energy is the energy of motion. Potential energy is stored. All chemical bonds are stored energy. So every time a bond is formed, it takes energy, but it also stores energy. Okay, so there's where the chemistry comes into play. If you have a molecule, you have energy that's been stored inside of those bonds. All right, here's the physics equations, which I do not care about. The kinetic energy is 1/2 the mass times the velocity squared. I'm sorry, my bonds are not moving that way. So, okay, but those are probably the ones that you're most familiar with. I am talking about the same kinetic energy. I am talking about the same potential energy. But do you see there's different equations to relate them together? Yes, these work, but those aren't talking about chemical bonds. So as long as you recognize, oh, potential energy and kinetic energy. So what kind of units are we going to be playing with? The SI unit is the joule, okay? You rarely will see joules out in the world. You'll see calories. You'll see British thermal units on your heating unit. I mean, there's so many different, but the joule is the one that is the SI unit. Okay.
They were about that in, fluids.
Yep. And then you were probably going a kilogram meter squared per second squared, which is different from a Newton, which is a kilogram meter per. Once you see them all put together, you're like, why do you have different names for things? Yes. Watts. Ooh, okay. Now that goes one step different into power. Okay, so that's the harnessing of the energy to do work. Okay, and that is just physics. Yeah, I don't care about that one. But yeah, that's, if you will, another term. All right, and then of course, calorie is, we just can't get away from calories in America. It's just always going to be there. In fact, if you look at any label, they do not list them as joules. They list them as calories, and it's just never going away. It's like gallons. It's just too ingrained in our society. Yes, which is then converted to kinetic energy in the form of heat. That's exactly it. And just didn't, no, most people wouldn't even notice.
Doesn't the body burn calories with fuel?
That is exactly what it is. And so your body requires a certain number of joules to function each day. We just use calories instead of joules. And in the winter, it requires more, because where does most of your energy go? To regulate your body temperature. And in the winter, it takes a lot more to regulate. So yes, that's exactly where the calories come from. Well, and your body knows this. So in the winter, you tend to really like soups, gravies, really fat things, because it supplies more energy. It gets more bang for the buck. Where in the summer, you don't want to have that heat energy. So you eat things that are lower in calories because your body doesn't want that extra energy. So potatoes, gravy, soups, breads. Who craves ice cream more in the winter than they do in the summer? Because ice cream is full of fat, which has double the amount of calories as carbohydrates. And so your body's saying, okay, it's cold, but it'll give me double the amount of energy later on. And the same, it knows. Oh, your body knows. Ice cream is the way. So snow cones in the summer, ice cream in the winter. Just saying. Have your cake and eat it too. Yep.
It's funny how much the body knows.
Oh, wait till you take organic. Okay, who always relates rice and fish together? They just go together. Your body says, oh, those go together. How about corn and beans? You're not a Spanish or Mexican food eater? Okay. How about, okay, sorry, Americans don't have good combinations, but, so Asian is usually some kind of a fish and a rice. Spanish, is usually a corn and a bean, or a rice and a bean tortilla. Tropical is usually a fish and is it called yuca? So when you get into nutrition, your body has to have the essential amino acids, the essential fatty acids, and enough calories to supply the energy. And each type of food will supply different pieces. And so your body will crave the combinations that it needs. You can't get them all from fish, so you have to add something else in there. You can't get them all from corn, so in your region, your body will crave the food that it gives it. Because it takes more energy to cool down. It is the weirdest. But it takes energy to cool your body down, so you're using so much of your energy. Yeah, I know. Weird. It's completely weird.
My body doesn't tell me when I'm so I probably do my
Needing something and you just didn't know what.
I have no idea.
All right, and so internal energy, again, this is another physics thing, but there is a specific amount of energy in the universe. You can convert them back and forth, but you can't just create energy. You can't just destroy energy. Okay, there's your first law of anything. Your first law of thermodynamics says energy, okay, this is the Joule phrasing, anything cannot be created or destroyed. It can merely be changed from one form to another. Okay, you're not creating anything new. You're not destroying it. It can merely be changed. Can you change mass to energy? Yes, but you can't just destroy mass and you can't just destroy energy. And so that's the first law of thermodynamics. All right, so as far as thermochemistry is concerned, we have to just give you some terminology. And so there's something called a state function. If you're going to talk about energy, we are not going to talk about the entire universe. Okay, so that is too big of a system. So a state function is a property of a system that depends only on its present state and not how it achieves. Okay, so present state, not necessarily how it got there. So for instance, you're all sitting in class today. We only care that you're in class. Do I care that you came here on a bike? Then you came in a car, that you left at 10 in the morning, that you left at 6 in the morning. A state function means I just care that you were in the room. And I don't care what happens after you leave the room. My system is this room. I don't care how you got here, but once we're here, you're my variables. Okay, so that's basically a state function. A system is the area that is involved. So for us, this classroom is our system. Anything outside is not applicable. Can you exchange with the outside or the surroundings? Yes, air can go in and out. Okay, light can go in and out. Bodies could go in and out, but they're exchanging from our system to the surroundings. So you always have to define your system and you have to define your surroundings. So in a laboratory setting, your system is usually your beaker or your test tube or, you know, whatever your reaction vessel is. Heat is very different than temperature. Heat is a unit of energy. Heat is energy that flows into or out of the system due to a difference in the temperature. Temperature is a reading of an average kinetic energy. Hey, what's the temperature in the room? You go to the thermometer and the thermometer has an average of all the particles hitting it at that moment. Okay, it's not a true reading, it's just the average of whatever is hitting it at that moment. Where heat is the total amount of energy that's flowing, we don't have any piece of equipment that will measure heat. But we do have a piece of equipment that will measure the average, and we call that a thermometer. We call it a thermometer. So if heat, okay, and for us it's temperature, flows out of the system, we call that exo. So exo means out. Thermo means heat. So exothermic means heat comes out. Endothermic means heat goes in. If you cannot transfer heat, that is a closed system. And then we're not going to play with it, but it's called an adiabatic system, which means if we were in a perfectly sealed room a perfectly sealed room and it could not transfer heat anywhere, it would never transfer between the system and the surroundings, and those are very expensive. It's hard to get, something that won't transfer. You called them insulated containers. Okay. Oh, how do you trap heat with an insulated container? Well, it takes special material to insulate because heat likes to flow from areas of high to areas of low. So we always have to fight this energy. Okay, and so temperature is the average kinetic energy. And then we have to, of course, have variables, and it's a Q. And I have never looked up why it's a Q. I'm sorry. Heat of reaction is given the letter Q, little q. So a minus means exo. A positive means endo. So if you have a heat of reaction with a positive sign, it means you had to put heat in. If you have a heat of reaction with a negative sign, that means heat came out. And think through lab and how many times, whoa, my beaker's getting hot. And I said, oh, it's exothermic because heat was coming out. Now, most of you didn't notice, but there were a few times that your test tubes got cold. Okay, I don't know if you're even remembering any of those times because it doesn't get really cold, it's just subtly cold. Those were endothermic reactions and it was pulling the heat from the air. Uh-huh. So you wouldn't call it thermic, you would call it exogonic. So gonic just means energy in general. Light is energy, so it's exogonic. Right, but it is reducing as light. So gonic is a generic term for just energy. All right, and last but not least, don't you have to have a variable for heat? And the answer is yes. Okay, well, we couldn't make up our mind. Should we call it Q or should we call it H? And we're going to blame the physicists for this one because you have to have variations on a thing. And so H is generic. H is generic for heat. Okay, so enthalpy, okay, enthalpy is heat. So exothermic means negative H. Endothermic means positive H. Depending on your conditions, it's also the letter Q. Yeah, why? I don't know. Someday I should look it up. Okay. Oh, you did. Why is it Q and H? Okay. That's it. We can blame the French. We can blame the French. Okay, the rest of the chapter, and I just want you to see it's not very long, is all number crunching. Crunch, 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 and crunch. It is a very short chapter. It will definitely be finished on Thursday. So what kind of a quiz are we expecting on Thursday? We'll definitely talk about the last chapter. None of this chapter will be on there. So it'll be all about the metathesis, electrolytes, and redox. Okay, so that will be that chapter. The elements that were on 81 through 110. Okay. Yeah, actually, it's 81 through 110.
Okay, we got 11 right.
And then I will eventually make up for that quiz that we missed. I'll figure out a way to get that in. All right, so exam 4 goes on tomorrow. Don't forget there is that study session for it. Exam 5 will go on the next week, and your practice problems for your practice final will be on Canvas that you will be able to work together if you so desire, but I guarantee if you can't do them yourself, it's not helping. But there is nothing wrong with sitting in a group and working through and talking. Well, why didn't my way work or something? And then, yes, you are more than welcome to work with Corey, but she has been told it's a very careful, you're helping on these questions. it's not answering these questions. But there is nothing wrong with working together with her and you're just working, and if you have a question, you can ask me things
So then 5 opens next week.
All right, did I answer everything that needs to be answered?
Hopefully.
I brought baby bunnies to lab today. Okay, my organic student has them, but when he gets done babysitting them with his kids, I'll bring them up to the person.
So we don't. Again.
81 through 110. 81 through 110.
Very good getting turned by those.
If only that one.
It's the hardest ones on the periodic table, you know.
Hope we're not doing all those for just 5 times. That's
I'll figure it out.
Could we actually add that extra, can we just add more questions about the elements to make that ones for the systems?
Oh, so just kind of combine it for this next one.
Yeah, but like, make this quiz worth 20 points and have 15.
Oh, yeah. I'll extend the points just a little bit. Yeah, I like that idea. All right, so I think that these are all together. So, looks great when you talk about it. So I think we're doing I will have to. I know some of them like the last periodic. And then I think there's so just this quick. Thank you. Even though that your code, so you know what the canvas is going to have, you add it to code and. So it would translate what our. If all of them. So don't look at the code. Oh, okay, I was like. That was like. So I go to and make them work. Like some people yes. Oh, yeah, that's what I was thinking.
That was like really, pretty much, you know, I didn't know. Yeah, I'm like,